Good afternoon, everyone. Lovely to see all of you. Our semester is really passing by quite quickly. We're already at week 8, but hopefully now you're starting to feel more confident in your ability as programmers and algorithmicians. So as the start or end of the week as it is today, we have a historical figure for us, as always, and this is Andrew Yao. He was born in 1946 in Shanghai. He did a PhD in physics at Harvard and a PhD in computer science at UIUC, so pretty impressive. He is very, very important in the world of cryptography. He contributed a lot to the study of randomness, as well to an idea called Yao's garbled circuits. One or two other interesting biographical details about him. He is currently the Institute Dean at Tsinghua University and the Distinguished Professor at the Chinese University of Hong Kong. However, given that he was in America for a long time and had US citizenship, it was only in 2015 when he became one of a very limited number of people to actually renounce his citizenship on his return to China, along with another prominent prize winner, Nobel Prize winner, Tang Ning. So he did win the 2000 Turing Award, which is, again, the equivalent of the Nobel Prize in computer science. And that was for his contributions to the Dolev-Yao security model, which is a way of analyzing cryptography to see if it actually does what it says it's going to do. So there's our historical figure for the week. And just like last week, I want to remind you where we left off with another historic figure. So multi-Grammy award-winning Taylor Swift, born in 1989. Okay, we'll skip the biographical details, but remember the problem that we wanted to approach for this week was the fairest way to distribute tickets to her most recent tour. So how many of you have recently purchased tickets online? Oh, Rex, you're here. Great, I finally remember your name. I got it this time. So purchase tickets online. What about in person? How many of you have purchased a ticket to an event in person sometime? In your life? Okay, we have at least a few. So someone who has purchased, Nathan, you purchased a ticket in person in your life? Some point? That's fine, it doesn't need to be for Taylor Swift. We can't all make good decisions. So I've got a few questions about your ticket buying experience that'll help us develop some code for it. Okay, there we go. So tell me a little, how did it work? How did the company decide who got tickets? And tell me a bit about the event. What was it?
I went to Luna Park with a friend.
Luna Park, okay. And Luna Park's a very high volume destination in summer. It's a theme park. And how do they decide who gets tickets and who doesn't?
They had, I imagine, a limited number of spots.
Yeah.
I showed up and I bought one. And then they probably added my name to a list and had one less free spot.
And where did you stand to buy one?
In the line.
In a line, okay. And how did that line work? Was it the person at the back of the line got the ticket, or?
Usually the person at the front.
Okay, so what would you call that?
A queue.
Yeah, a queue, but there's another way of describing the line's behavior. First
in, first out.
First come, first serve, first in, first out. That seems like a reasonable way of distributing tickets. So one thing that you mentioned was we could use a data structure to represent the queue. What's one data structure that we've learned that might be able to support this kind of thing already that we've learned? Not something new.
We could probably, run some sort of algorithm on an array with maybe a counter that shows the current place in the queue.
That sounds pretty good. So option 1 is an array. So now I'm going to need a whole bunch of people down to the front of the room to help buy some Taylor Swift tickets. And if you're lucky, just like happened last semester, some of the people might actually get a chance to go. I'm not sure if she's coming back to Australia, but you never know. And Chen, you have a special role. You are going to be directing the line. So put that hat on, other way around. The little shiny thing should go at the front. Okay. So here is our array. Can you test the microphone?
Testing, testing.
Testing, testing. Great. Okay, that's great. So you're here at the ticket counter, and what do you do with your array?
So if you want a ticket, I will give you one, and if left, I'll get a 1 next.
So let's say this is position 0 in the array.
Yeah.
Zelfin, you can purchase your ticket.
Yeah. Give me money. Yeah, and I give it one of ticket.
And now what do we do? He's in array index 0.
And he should left, leave. Yeah.
Okay, so Zelfin, you can go sit down on that chair right over there. No, don't go back to your seat just yet.
Yeah.
Okay, wait. What are you doing? What happens now to the array?
The next one should come up.
Well, how does she come up? So she's in index 1.
Yeah.
So what should we do to the array?
Should we change her index from 1 to 0?
So we could do that. How do we change the index of something? Is there a way to do that?
Well, we like assign her to.
So we could do a copy. We could copy whatever is in index. Okay, so let's do that. Let's copy you from index 1 into index 0. Okay, we'll make a copy so you can move over 1.
We cannot duplicate people in real
Yeah, I know we can't. Is there another Sarah here? No, unfortunately, you're the only Sarah we've got. So let's just imagine that there's another copy of you in index 1. Are we done with our work?
Yes, for now.
Well, what about J? There's now like a blank space in the line.
Oh yeah, you are right.
So,
oh, by the way, if he didn't live, could we like swap them?
so maybe we'll try that after. We'll see what other strategy we can use. But for now, what do we do?
Okay, so she give me money. I give her the.
Okay, we can try that. Okay, Sarah, go down for a second. But now we're kind of stuck.
Yeah, kinda
Because now we've got like 2 copies of Sarah and Jay is over there. So Sarah, come back for a second.
Yeah.
So what should we do? It's clear we're not done with our work because we got stuck before when the second person left. What should we do? Well, Jay, what do you think? Let's give you the microphone for a second.
I'm not quite sure, but maybe we can just resize again so that's over here.
So if we resize the array and we just make it of size 2, then you just get cut out.
No, like, firstly,
Got to hold the microphone. Yep.
like
And close to your mouth.
we can use swap self-in with me, not me, but move self-in to n, like the last one, and move us like 1 step forward.
Okay, so let's forget the bit about moving Zelfin for the moment. Go back to your spot where you were in array index 2. Yeah, and you said, we should move everyone else down 1. So we're going to copy you from, what space are you in? And we copy you to 1. Yeah, so now you can move over. Yes. Yep, so Sarah's moved up to array index 0 and you're array index 1. Now, let's say that Finn comes along and joins the back of the line. Come along and join the back of the line. So what are we say in code? How are we going to do this? That's array index.
Oh, that's index 3.
That's array index 2.
Index 2, yeah, because they move forward.
Yeah. Okay, let's pass the microphone back. Okay, and now let's continue with our service.
Okay, so I give her 1 ticket, and he should leave.
Well, she doesn't really leave as much as what happens instead.
Oh yeah, actually, the person in index 1 just copy to index 0. Yeah.
So Sarah actually becomes J. So let's do that copy.
Yeah.
Do.
Yes.
Are we done?
No,
Thank you, Sarah.
Oh yeah.
Okay, what do we have to do?
So I still continue to give tickets.
Wait, we've forgotten. We've left Finn out there with a blank space.
You are right. So Finn also need to copy to index 1.
Yeah?
And so we move 1 step forward. So I think right now it's done.
Now we're done. Okay, and let's do the rest of the tickets.
So I give 1 other tickets, and then yeah. So I need to copy him to index 0.
Yep.
And yeah. So you actually became Finn right now. Yeah. And
Thank you, Jay.
Another ticket.
Yep.
And I think it's done.
And then we're done. Okay, so that looks pretty good. What was not so good about that? What was annoying?
So you have to like continues to copy everyone like except the index 0.
Yeah, and what if we had 100 people in the array and we give a ticket to the 0th person? How many copies would we have to do?
It's so every time it's n.
Yeah, we'd have to do big O of n copies for every time we take something out of the front. So that's not very good. Okay, everyone who just got a ticket, come back and line up again. Finn, you were at the very back. Zelfin, you were at the front. Now let's try your other strategy that you suggested, which is maybe like we just keep track of where the front of the line is.
Yeah.
Okay, so maybe Finn, go down for a second.
Yeah.
And let's say we have an array of size 3. Okay, so let's start our ticket process again, only now we're keeping track of where the front of the line is.
So
Front of the line right now is Zelfin, because he's the first person in array index 0. So let's give him a ticket.
and
But he's no longer at the front of the line, right? He's already got a ticket. So where's the front of the line now?
so the front line will move to index 1.
Yeah, okay, so move to index 1, where the front of the line is.
Line will be index 1.
Yeah.
So I give her another ticket.
Yep.
And the run I need to move to index of index 2. I'm currently index 1 or index 2.
0, 1, and move along to index 2.
I give her another ticket, and I run I move to index 3.
Well, we said that there's only room for 3 in our thing. And now Finn comes along, and what does he do? Exactly. There's a bit of a problem. So where could we put Finn?
Oh yeah, so index 4.
So we don't have an index 4. So one thing we could maybe do is we could allocate some more memory. But then if we keep adding people at the end, we're going to keep adding more and more memory, and we've wasted all of these because there's no need for Zelfin to be standing here anymore, is there?
Yeah, you're right.
Right, so what else could we do? Where else could we put Finn?
Okay, so after we finish the first 3 people here, we just like free all of them.
Yeah, and then where would Finn go?
I will move Finn to index 0.
Okay, so now let's move Finn to index 0. Zelfin, you can go home. But now we've got this tricky thing where, where we need to keep track of how much of the array is actually being used and where we are in the array. So that gets complicated fast, and there's still a lot of operations that happen there. So maybe there's something better. So can we have a round of applause for Chen? And both of you can go home with your tickets. And now Ella is going to take the role of the police person. Go. You can take the microphone. Yep, put it on your head. Okay, so I'm going to need a bunch more volunteers. So remind me your name in the blue Melbourne Uni thing again? Jacob, okay, you're down to the front. Blake, do you want another turn? You haven't been in a while. On the end, remind me your name. Sharon, that's right. Sharan. Okay, Sharon, you're down at the front. Who else? Anyone else want to be down? Dominic, do you feel like it? Okay, Dominic, you're down as well. Okay, these are going to be your troops. And we're going to come up with a better way of handling our ticket situation. So you're in charge of all these fine, strapping young men, and we're going to see what we can make of them once Dominic gets here. So for a line, do you need to know exactly at what position everyone is? What are the things you care about in a Taylor Swift line?
Who has tickets and who...
Is that on? Hello? It's very, very quiet. So you're going to need to be your loudest self.
I care about who has tickets and who doesn't.
Yeah, so we really care about who has tickets and who doesn't, and what's a way of determining like who gets the next ticket? What's the piece of information we really, really need to know if you're the ticket person?
Who is next in line?
Who's next in line? And if someone new comes, what's the other piece of information we need to know?
I'm not sure.
Where the end of the line is, right? Because we need to be able to add them to the end. And so you don't actually need to keep track of like all the indices, do you?
I would hope not.
You probably not. If you keep track of the front of the line and maybe the end of the line, then that should be enough. Except we're missing one vital piece of information. So if you only know where the front of the line is, what problem do you have if that's the only thing you know?
Like, you don't know when it's going to end.
Well, you might not know where it's going to end, but how do you even get to the next person?
I'm not sure.
Well, here's my recommendation. So if the first person in the line knows where the second person in the line is, then you don't have to keep track of that. They can keep track of it for you. And that's Sharon. And then if Blake knows who's after him, And I've forgotten your name already. Jacob. Oh, you should have given me a second. And if Jacob knows who's after him, then really all you need to know is the very, very first person. So as long as you know Sharon, and Sharon knows Blake, and Blake knows Jacob, and Jacob knows Dominic, then we're all good. So now let's actually see if we can represent this in our computer's memory with something new. So behind you, Ella, you will see a pink bag on a chair. Yep. And inside the bag, there will be some, do you want to, yeah, that looks pretty good. Okay, so the first thing I'm going to have you do is separate out one of them. So take it. So this is going to be what we'll call a linked list. And the basic idea here is that every node or every individual in the line, all they have to know is where the next one is. So right now, Ella is assembling for us what we will call the head of the line. It's just a fancy computer science word that we use sometimes instead of front. So tell me what you have there. Explain to everyone, show it nice and high.
It's a plug, one end can connect to another outlet.
Yeah.
Yeah.
So, and who is the head of our line? Sharon. That's okay. So why not, let's give him the very first node.
This one.
Yeah, you know where he is. He's going to be the one that keeps track of the next thing. So give him the whole thing.
Oh.
There we go. Right? Now, Sharon, what piece of information did you need to know to make this whole thing work? You needed to know one thing.
What's the method on the line?
No, she knew you were at the front. What did you need to know?
Well, I needed to know who was in front of me.
Well, there's no one in front of you.
Yeah.
But what other piece of information? You were close. Yeah, who's behind you, right? So we can draw a link from you to the person behind you. And let's do the other end so that Blake has some way to plug in. And now, Ella, if you want to go along, and we can figure out how to, might need some help. Okay, let's untangle this. There we go, this is good. Okay, so let's build out the rest of our structure.
So can I move up one index?
Yep, you can move up because we can follow the link from Sharon to Blake.
And then I give Blake the wire.
And now what information does Blake need to know?
Who's in front of him?
Yeah, or who's behind him. So there we go, there's one for you.
Then I'll move another index up and give him
That's Jacob.
Jacob.
You don't know where Dominic is?
Yeah, although you'll need to be clever with your plugs, I think. So you'll need to switch that piece out, I think. I don't know. There we go, switch the wire. Some teething problems with the demo. Now you can plug that in. And we'll save our last two links for a little later. So this is our basic structure. It seems to work pretty well. Okay, so let's just assume already, for argument's sake, that we've already built this thing. We'll get into how to actually construct it momentarily. What piece of information, Ella, do you know? The one piece of information you know.
What index on that?
No, this is not an array.
Oh. I don't know how many people I've passed.
You're only keeping track of one piece of information I said, and that's all you need to make the thing work. Yeah, who's at the start? So all you need to know is Sharon's identity. Okay, so let's go back to put you at the front, and Sharon, let's bring you further over here. Let's spread you guys out to represent different places in the computer's memory. And Ella, you can come all the way to the front here. Don't need you to be trapped behind the list you've created. Okay, and now what we want to do is traverse the list. So let's say that at every stage of the list, we're also going to allow the different people in our list to contain a piece of data. And that's what we're going to store in our list. So for now, let's say all of you are storing the month in which you were born. So that's the data we've put inside your heads. And now I want you to find out all the different months that you have stored. So how do we go about doing that? If all you know is Sharon's identity.
Well, I'm going to ask Sharon what his birth month,
Yep.
birth month is.
And you can answer, Sharon?
July.
Okay.
And then I would get Sharon to then ask.
Well, Sharon's inanimate. He's not really a person. So you're the one that has to do the work. But Sharon's holding something. He's holding a link, right?
I can follow the link to Blake, was it? Blake, what is your birth month?
October.
October.
Okay, now what do we do?
Follow the link again to Jacob. Jacob, what's your birth month? February. Follow it again. What's your name? Dominic, what's your birth month? August.
Very good. And now you're still only keeping track of where Sharon is, so let's come right back to the very front, plus the variable that you were currently looking at. So that was a really good job. So let's look at that in some code. Let's see here. So we really needed two pieces of information for this to work. We needed every node to have the piece of information that they were storing, so that was their birth month, and we also needed a link to the next node. So this is just a structure. There's nothing particularly special about it. This is not called a linked list node. This is something that we've invented, or really that Ella has helped us invent. So we have one other thing that we mentioned earlier. There's a slight challenge here. Because our node has a node inside of it, that's not going to quite work. What we actually need to do is we need to add a forward declaration of what a node is up to the top to just warn the compiler. So when it sees a node T for the first time, it already knows. So that's our basic code for the node. I'm going to open up a new bit of code here. Let's see. And Ella is going to help one more time explain to me how she traversed the linked list. So let's say that we have typedef struct node T, and then struct node and we don't know what data T is. We'll have to type def that as well. So let's make that type def data T, and we'll just make that an integer because an integer is good to hold the birth month of someone. Okay, so now let's write a function, and we'll call this print birth month. And in it, we will take a pointer to what piece of information did you need to know?
Who's at the start?
At the start, and what do you remember what word we used for that? Opposite of tail?
Head.
Head, yeah. So that would be the head. And that, what type is it, given our?
Node.
Yeah, it's a node. Okay, so it's a node T, and we will call that head. And then what was your process? Remind us all.
I went to the head of the linked list.
Yeah?
And then followed the connection from the first of each nodes.
Yeah, they're nodes.
Yeah.
Everyone's a node.
Follow the link from that node.
So before we followed the link, what did we do?
Oh, sorry, ask the birth month.
Yeah, so we did printf, that's right, birth month is, and we can do, remember this syntax to access the member of a struct. So that was the first thing we do. And then what do we do?
Then
You had it a second ago.
we follow the link.
Follow the link. So let's have a variable that keeps track of what link we're currently looking at. So let's make this a node T pointer type. And that will be current. And we'll start off at the head, right? Because that's the first one we know. So after we've visited the head, what do we update current to?
Plus.
Well, +1 is just a number, and this is an address.
Sorry, they pointed to the next node.
Yeah, so how would I finish this line?
Equals point. Do you use a dereference?
Close. I mean, to get the element of a struct pointer, we can use that. So Sharon is stored in which variable currently?
Current.
Yeah. And he has a property called next, right? So what would I write here?
Current equals next.
Current equals current arrow next. Okay. Are we done? Does this get everyone's birth month? Does this get everyone's birth month? No, what am I missing? All this does is it gets you one step. That gets us to Blake. And then what happens?
Repeat.
We repeat it. Okay, so how do we do repetition in C? A for loop. Or we could use a while loop as well. So we do need one other piece of information, which is when our loop should end, right? So Dominic, what happens, what are you connected to?
The end loop.
Yeah, and what's out there? Nothing. Okay, so what do we normally use in C to represent nothing?
A null byte.
Well, a null byte for a string, or when we're talking about pointers? Very, very similar. It's the same word.
Null.
Yeah, we use null. Although just a side point of interest, null as in null byte is normally one L, and null as in null pointer is normally two Ls. That's, I know, confusing, spooky, but that's how it works. So we end a linked list just by having the very last element and setting its next pointer to null. So now that gives us the last bit of code, or the last idea we need to finish writing our code. So you said a loop, right? Do you think a while loop would work?
Probably a while loop.
Okay, and what are we checking?
If the current element equals null.
Well, while it does equal null, while it doesn't equal null. Okay, so while it doesn't equal null, do that. Let's put that in there. And ta-da, you've just written your first linked list code all by yourself. You didn't even need me for that. So can we have a huge round of applause for Ella for discovering how to do linked lists? So if we go back to the slides, here is something that I prepared earlier. And this looks almost identical, except instead of saying exactly what we're going to do, I just have a function here that allows you to process it. So in process, that could be print, it could be do some calculation, it doesn't really matter what, but that's the basic idea here. So we still have a few more operations to do. So the next one we have is how to add someone to the front of the linked list. So I need another volunteer. Madeline, how are you feeling? Do you want to come down? No? Okay, Toby, you haven't had a chance in a while. So we want to add Toby to the front of the linked list. Toby, come all the way over here just so we can keep track of you for the moment. Wait. Yep, just hang out here. Okay, Ella, how do we add him to the front of the linked list?
I am thinking.
Okay, what piece of information do you know?
I know that Sharon is currently at the front of the linked list.
Yep, and Toby's just come in, so presumably we know his variable as well.
Yeah.
Okay.
I mean, ideally, I could just expand the size of the linked list.
Well, remember, the linked list doesn't really have a size like an array does. You only know one piece of information about it, which is who's at the start. So let's imagine that we've already added Toby to the list. Who's at the start of the list?
Toby.
Toby, right? That's if we're doing a list that we're adding to from the front. You could also imagine it where we push someone to the back of the line, right? So adding someone to the front of the line will get you some very angry concert goers, but let's do it for the moment anyway, and then we can try the reverse. Okay, so given that Toby's going to be the new front of the list, you're probably going to update one of your variables, aren't you?
Yes.
Which is?
The head.
The head. We're going to update the head. But before we do that, let's just say Toby is the new head, and that's all we do. Now, how do we get from Toby to the rest of the list?
We'd have to establish a link.
Yeah, and we would have had to do that ahead of time, because if we update Toby to be the head of the list immediately, there's no link here. So you've got all the ingredients you need. What do we do?
I give Toby a link.
Yeah, so that's the very first thing we do. And we do Toby-next equals
Sharon,
Yeah, but Sharon was the what of the list?
the head.
He was the head of the list. So Toby.next or dash next with a little arrow thing is Sharon. And now what's the other change we have to make?
Make Toby the head.
And now so we make Toby the head of the list. So that's exactly what we have there. So let's say we make a new node. We're going to malloc it. Let's just check that malloc worked, fill them with some data. And then these last lines, 7 and 8, are the important ones. So we connect his next to the previous head of the list, and then we just make him the new head of the list. So we're returning it and saying whatever we return from this function is the new head of the list. So that's good. Okay, let's disconnect Toby. Yeah, you can still keep your side. Yep, pass it on, back to Toby. Okay, so what if we want to put Toby at the end of the list? What's the process?
We would have to, find who is at the end.
Okay, so how do we do that?
We follow all the links
Okay, so let's talk through it just a little bit more clearly. Where do we start?
at the head of this list.
And then we
follow the link from the head to each.
so dash arrow next, arrow next, arrow next.
Arrow next, until we reach the end of that loop when we're checking if null.
Yep.
Current character.
So give me that in code. So if this is current, sorry, Dominic, you're now current. Current, what check do we do?
If current equals null.
Well, does he look like null to you?
No, he doesn't.
Okay, but where's he pointing? What's he attached to?
Next.
Yeah, so current,
Pointer
current funny arrow symbol next.
equals null.
Yeah,
Then link. Can I call it the tail? Is that a technical?
we could call him the tail and we could keep track of the tail as well, and that'll be a very useful way so we don't have to do this every time. But for now, he's just current.
Okay. And then we connect current to
Toby or new or whatever it is. And then do we have to update the head?
No.
No, we don't have to update the head. It's still the old head. But if you were keeping track of the tail as well, which you might want to do, then you'd update the tail. Okay, so now we've added someone to the list. That was a great job. But now we have one other operation that we want to do. And I flashed it on screen accidentally. But come over here. And now we're finally at the point where we're ready to start our ticket sales. Toby's lined up as well. And we want to serve Sharon. So how do we do that?
I give him, he gives me money, hopefully. I give him a ticket.
Well, you going to give the money or no?
That's fine.
Take money, then I would follow his link to the next node. Take Blake's money.
We're only doing one ticket for the moment.
Oh, sorry.
Yeah, you only have one ticket. More tickets will come later. So we give the one ticket to Sharon.
Yes.
And now what do we do with our linked list?
Nothing.
Is he still at the front of the line?
Oh, no.
Yeah, so what are we going to do?
We're going to kick him out.
Okay, how do we kick him out?
He's going to voluntarily leave.
So he's currently head. He's feeling very self-important.
Yes. I'm going to move head to Blake.
So how do you do that? Step by step. So the first thing is we're at Sharon. Sharon's the only piece of information we know.
Yeah.
So what's the first thing we do?
Aside from giving the ticket.
Yeah, we'll give him the ticket, but now how do we get to the new head?
We go to the next.
Go to the next. Yep.
And then assign him as.
Yep, so now Blake can be the new head.
Yeah.
But Sharon's still here. What have we forgotten to do?
Beacon.
Well, how do we kick things out of memory in C? Not quite. He's been imprisoned inside the computer's memory. Opposite of malloc. Free. I heard it out there somewhere. So we free Sharon. So in order to free Sharon, we can't, even though we've moved along one, we actually still need to keep track of his variable until the point at which we free him. So that's going to be what we see here. So let's go wind you back for a second. Right, we know where our head is, and let's call that P for the minute. Let's create a new variable just to keep track. This is a temporary variable. We'll call it old. Now what we do is we just check that everything's right so far. That's our assert statement. So old equals P. So we're storing whatever Sharon's value was previously into old. Then we do what's on line 6?
P then turns to next.
Yep, so we move along to Blake.
And then we push Sharon to
Into the void.
Yeah.
Yeah, so Sharon, you can go off into the void. You don't need unlink, just drop it. There we go. And notice the interesting thing here is that if we hadn't freed, even though the new head was here, Sharon would technically still be alive. But thankfully, because we're freed, he's now back in the ether where all good students belong. And the other thing here is you'll notice at the very end of this code, what I've actually done, I've returned P, which is just the new head. We can do this one other way, where instead of having to do this thing where we update the head carefully, we can actually keep track of the list as a whole. And so instead of having to return the head, what we can do is just update the pointer that the first node of the linked list is pointing to. So there's a way of doing that as well. Not so important. Okay, let's see what the time is. We've still got a few more minutes. Okay, so Ella, do you want to turn around for everyone? Why do you think we're using malloc in this process? Why not? Why do we need it in the first place?
Because we're not sure what size the linked list will come to be.
Yeah, we're not sure what size the linked list is. And say we start off with these people. What happened when Toby came?
We had to, free up space and add strings.
Well, we didn't have to free up space because we weren't removing anyone, but we needed to add some space, and we don't know how many people are going to come into this line. It might be 10, it might be 100, it might be 1,000. And this is a way that's an alternative to an array that allows us to kind of keep track of things coming in and coming out. So what two functions do we actually need if we want to represent a queue, like a real life queue with people coming in and people going out? Like a normal queue. Yeah, like think abstractly. It doesn't have to be C functions. What two things do we need to be able to do to the queue?
We need to...
You can handball it to Blake if you don't want to.
we need to move through the queue. We need to add people and remove people.
So where do we always remove people from the real life queue?
From the front.
From the front. And where do we add people?
At the back.
At the back. So there are our two functions that we need for our linked list to really be called a queue. And this is an example of what we call an abstract data structure as well, because it doesn't really matter whether you did this using an array or you did this using a linked list. We saw that you could do it both ways. To actually represent a real life queue, all you needed was to write these two functions, some way to make sure that you could serve the person at the front and that you could always add someone to the back. So despite the fact that Ella and Chen took very different approaches, they're still ultimately doing the same thing. Now, do you remember what the disadvantage of Chen's approach was? He was using an array.
I'm trying to remember what his...
So what happened when we removed someone from the front? What did Chen have to do?
That variable was deleted.
And we did this copying thing, right?
Yes.
Do you remember how many copies we did?
And copy.
Yeah, we did n copies. Okay, and so that's if we want to remove someone from the front. How many copies do you have to do if you want to remove someone from the front?
0.
0. I mean, you still have to do a little bit of work, but it's the same amount of work, and it doesn't matter how many people are in the back of the queue, does it?
No.
Right? So you do the same amount of work, so that's equivalent to big O of, do you remember this? Okay, what is let's say you do 5 steps, right? Every time, that's big O of, it's big O of 5, right? And 5 is 5 times 1, so that's just a constant, so it's big O of 1. So that's a big improvement over our big O of n for Chen's thing, despite the fact that it's the same abstract data type. So what this tells us is you can have a queue that runs in big O of n time to add someone to remove someone from the front, or you can have a queue that runs in big O of 1 when you remove someone from the front. So it does come down to the implementation details of your abstract data structure. So what about adding someone to the end? How long does that take you at the moment? Let's say there are n people over here and one more person comes along.
Just n plus 1.
I have to say that a bit louder.
N plus 1.
So, which is really big O of
N.
big O of n, right? So you have to go all the way, follow each of the links until you get to the very end. But you had a better strategy. You suggested something before to me around Dominic.
Oh gosh.
You called Dominic something else
I call him a null.
other than a null, because he's not a null. We value Dominic greatly in this class.
A tail.
A tail. So if you kept track of the tail as well as the head, how quickly could you add someone to the end?
Very. O of 1.
O of 1, yeah, that's great. That's exactly the right answer. So by just adding a small bit of extra storage that you keep track of, you could make both of those operations big O of 1. Now, so removing someone from the front and adding someone to the end could both be done in O of 1 with a slight implementation tweak. Yes?
Doesn't figuring out the tail take n times the first time you do it?
Okay, let's pass that back to Ella, and I'm going to let you answer this question, because you've been thinking about this problem really hard.
I mean, that'd be correct, right? You have to first.
So let's say we add someone to the end. How many steps does it take us to fix the tail?
We know where the tail is?
Yeah,
O of 1.
yeah. And presumably at the very, very start, when the only person in the room is Blake, we know where the head is, right? Do we know where the tail is?
If it's just Blake, then the tail would also be Blake.
Yeah. So that was only one step to figure out the tail is, and every time we add someone, it's only it's only big O of 1.
Yeah.
So really, how much extra work is it for us to keep track of the tail?
None.
None really, like big O of 1. It's a tiny, tiny amount when we add someone to the end. There you go, you've answered Jack's question perfectly. Do you want to take over the rest of the lecture?
I'm perfectly okay. You're doing a great job.
Okay, so what about a stack? Now let's have the same thing. Sharon, do you want to come back just so we don't have this dangling on the floor? What about if we're representing a stack of pancakes? So how does a stack of pancakes work? What operations can you do?
Take one from the top, eat it,
Yep, and what's the other thing you can do if you have more pancakes in the pan?
add them,
To the...
stack, add them to the top stack. Yeah.
And how do you add something to the stack? Does it go on the bottom?
No, it goes in.
Goes on the top. So in our representation, what do you think those two operations are? So where do we remove something from?
The first.
Yeah, so we can remove the first thing. We can remove the top pancake. And where can we put a new pancake?
In that same position.
Yeah, in the first one as well. So remembering that we had these two functions, insert at tail and extract from head, what would these be for our pancake example, for our stack?
Extract from top of a pancake stack.
Which is, in our linked list, it's also the...
Head.
Yep. And where do we insert?
Insert at head.
Yeah. And so that is the difference in the abstract data structures for a stack and a queue. They're really very, very similar. It's just insert at head, extract from head is what makes a stack. And insert at tail, extract from head is what makes a queue. And so really, we've come up with a way that using linked lists, we can implement both a stack and a queue just by determining what additional functions we're going to allow the user to run. So you can delete your insert at tail function, and then you've essentially made yourself a stack. And so can we have a giant round of applause, particularly for Ella, but for Sharon, Blake, Jacob, Dominic, and Toby, who wonderfully demonstrated linked lists for us. And one more extra round of applause for Ella, because I think she did such a superb job. Okay, you're all free to go back into the void. Thank you very much. Yeah, and you can put the cables back at the back. So with that, I hope you have a wonderful weekend. We'll leave that there. I hope you enjoyed our exciting demo of linked lists. I will see you all next Friday, but there's still a lecture on Thursday. See you all later.